Okay, I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students I have here. I pray that you just add to our understanding today. Help us to, again, Lord, glorify you as we study your creation. Lord, in your name I pray. Amen. All right, so thank you for your homework. I will now dive into Chapter 10, which is about conic sections, polar coordinates, and parametric equations. I would say that's probably in order of increasing importance. Well, I don't know. I mean, it's hard to judge what's most important, but I'm just starting with conic sections because that's at the start. Now, conic sections, important topic. They give us a few nice examples to bounce off of as we're studying these more general ideas of polar coordinates and parametric equations. So I'll start with the idea of a conic section. Now, so there are three kinds of conic sections. There's a parabola, an ellipse, and a hyperbola. I suppose there are also lines, but whatever. Why are these called conic sections? Something to do with a cone. What's that? But a cone just looks like this, right? So how can you get a hyperbola from that? Oh, you mean yeah, okay, so. Yes, of course, Mackenzie is correct. This is actually a cone. You guys who thought that I was right to start with are all wrong. A cone is always a double cone in math, right? I mean, this is a cone to a mathematician, all right? So I guess in view of this, it makes the whole idea of eating a snow cone really difficult. Yeah. What's that?
Without the bottom cone, you're saying that without that bottom part, it's not a cone.
I'm saying the whole thing I just drew is a cone.
What did you say that we got wrong the first time?
That you thought the top half was a cone.
Yes.
No.
It was not a cone?
I don't know. There's like two uses of the word. There's two uses of the word, right? Like there's the common the common everyday speak is that's a cone, right? But mathematically, if I talk about a cone, I'm including this and that. A semicone? I don't know. The point is, if you can imagine taking this cone, right, and you can imagine slicing a plane through it, right? There's three different things that can happen, right? One of them is that you just slice one of the semicones, using your terminology, right? And if you do that, if you can envision a plane intersecting the cone, what you'll get is an ellipse, all right? If you can imagine a plane that cuts through, like, two different, that cuts through, maybe like this is better. It cuts through like that, then you'll see you're cutting through two different disconnected arcs. That would give you a hyperbola, right? And then I think the parabola you get from, what's that? To the top, like, oh, just like that? That gives a, yeah, right, that's a parabola, yeah. Very good. Anyway, so this, this word section, what does it mean? It just means to cut, right? So, like, I used many of you have seen movies where a good guy has, taken a section of one of the bad guys or something, right? You cut straight through him, and then you can see. Okay, maybe we don't watch such movies, but anyway. If you have seen such movies, sometimes you'll see a section being taken of a villain. So, anyway, violent movie analogies aside, these are your conic sections, your standard. So in each case, I have written the standard equation, all right, and the geometric definition. Let me discuss these. So I'm assuming that the conic section is set up in the xy coordinate in the standard orientation, just to start with. So parabola, the parabola is formed from two things: a directrix, which is a line, and a focal point f. All right, and the equation is something like this: x squared is equal to 4cy. where c is greater than 0. I mean, usually you write this y equals like some constant times x squared, right? Or something like that. With this setup, where's the origin? I suppose the origin's... Well, I mean, the origin for that picture... Sorry, I'm trying to find an equation here. There is a typo in the book. F is on the positive y-axis. The directrix, L, is horizontal. F has coordinates of the form c comma 0, with c greater than 0. No. I mean, if this is the picture, right? The focal point is on the positive y-axis. What does the focal point's coordinates look like? They're 0 comma c, right? I mean, if this is the y-axis, all the points on this have 0 comma stuff. There's a little typo here in the book. Let me not be distracted by it. Let's go on here. That actually, c comma 0, I believe, would be if the directrix was vertical and you were looking at a... No. Well, sorry. Let me stop being bothered by something. Who cares? The book can say what it wants. Let's go on. So this is a parabola. It's formed by the collection of points which are equal distance from the directrix and a focal point. So what's the distance from a line to a point by definition? It's the shortest distance, right? So you drop a perpendicular bisector to the line. The length of the line segment that's formed by the perpendicular bisector from the point off the line to the point on the line which it meets, that's the distance to the line. That's d2. On the other hand, d1 is just the straight line distance from the focal point to that point on the parabola. If this is a parabola, then d1 is equal to d2. And that relation is held as you trace along the parabola. It's the collection of all points which are equal distance from a focal point and a given directrix. All right? Now the section, it goes into some detail about something really pretty about the parabola, right? Which is that if you study the reflection of light rays off a parabola, what happens? Like, if I have a light ray that comes in here like this, right? And then if the angle of incidence equals the angle of reflection, which is how things work, right? Optics, then the light ray comes out like that. If the light ray comes in like this, it comes out like that. So the point is, this parabolic reflector, it has this property that it takes light rays coming in at these different angles and it reflects them back out parallel to the axis, right? That's why we use parabolic reflectors for like headlights. It gathers the light that's created by a little bulb and it focuses them in that one direction. So that the mathematics of that is worked out in this section. I won't work it out, but you can read it. Anyway, any questions about parabolas before I resist the urge to make my picture more cluttered? So an ellipse, right? It has two things. It has two focal points, F1 and F2, all right? And I need a volunteer. Let's see here. Who should I harass? Mr. Thompson volunteers? All right, I'll allow it. What's that? Am I gonna do? All right, let's see here. So you take these and just pick 2 points, say like this point and that point, and hold the markers out of the board. Fixed at those points, all right. And then I'm going to slide this under here like so, and then put it back. Now don't let this slide off. All right. Got it?
Yep. Whiteboard's not the best source of friction. The whiteboard's not the best source of friction.
Yeah, no. That's why it's inferior to chalkboards, among other reasons. All right, take it off. So what we're doing there is creating an ellipse. The reason this works, here you can go. Actually, well, you get there. That's yours now. All right. I keep the markers though. So the way this works, right, is at any point that we were up here, you had the necklace there, whatever you want to call it. You had this distance, d1, this distance, d2, and this distance was fixed, right? So there's always that little bit of the necklace which is stretched between the focal points, f1 and f2, but that's the same at each point all the way around this thing, right? So what we have then geometrically is the sum of d1 and d2 is equal to a constant at all points around this shape. And so that's how you define an ellipse geometrically. It's that the sum of the distances between the 2 focal points is held constant as you look at an arbitrary point on the ellipse. Right? Collection of all such points. In particular, the relation between that distance and the standard equation is as follows: d1 plus d2 is equal to twice a. A is a comma 0 is the coordinates of the vertex of the ellipse here, like that. Okay. And then like 0b and 0 minus b, these are the vertex. These are as I have it drawn here, this is the semi-minor axis. That's the semi-major axis, right? If there's a longer one or a shorter one, we can define those. And then another thing which is worth mentioning is this notion of eccentricity. Now he has this, your author, the text has this buried in the exercises. I think that's unfortunate. Eccentricity is one of the first things I want to talk about when I'm talking about an ellipse. Because what's the most important kind of ellipse that we know about? What's that? Like, for example, what if the necklace is broken, like this, and then I can only do here. I'll shorten it slightly. Right? If I go, yeah. If you look at the outer edge, you got a circle, right? There's just one focal point. Oh, here. Oh, I guess it's no one's. I was told not to throw those at people, they hurt. By someone. But anyway, my point is, the case when it's a circle, the 2 focal points, or how do you say FOCI? What do you say? Say it again? Foci? 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 I don't know. I think all of these sound wrong to me. So you'll notice that I always say focal points. Foci. All right, let's get back to making math great again. Let's see here. So if the 2 focal points become the same point, yeah, I know. If the two focal points come to a single point, right? If they're identified, I don't disagree. I just don't like the word. If the 2 focal points become the same point, then you have a circle, right? And it's nice to have a way to explicitly characterize that in terms of a variable. That's what the eccentricity does. Eccentricity is the quotient. It's the ratio of c divided by a. Now c is the distance from the focal point to the origin. in the standard presentation, these focal points have to be equal distance from the origin, okay? That's part of our setup. We choose the origin to be the middle of the ellipse. All right. Of course, there's nothing stopping you geometrically from shifting the ellipse this way or that way, or you could do this. You could rotate it, right? Then you get equations like this. Actually, that's not an ellipse. That's a rotated hyperbola. You'd be like, how do you know that? Well, it's 1 over x, right? 1 over x is a rotated hyperbola. Yeah, if you, that's a hyperbola. And this time the asymptotes are actually the xy axes. Now I'm getting ahead of the story. We'll get back to this. Anyway, rotated conic sections are above our pay grade in here because we do not have the requisite mathematical skill to properly understand these things. The skill that you need is called diagonalization and the study of quadratic forms. This is one of the things we learn in linear algebra, or 221. That's like next week. Yeah. Michael's like, no, enough new material for one semester. Stop adding new things. Why? All right, sorry. There's a window inside 321 for you. Anyway, so the eccentricity is c over a. If you look at c could be 0. That's the case of a circle, right? So if c is equal to 0, we have a circle. That's when the eccentricity is 0. But otherwise, of course, c has to be before a in this picture, right? And anything else would be nonsense. So c divided by a has to be less than 1. And there's your ranges. Eccentricity 0 is circular, and the further away you get from 0 and the closer you get to the 1, the more really cigar-shaped it is, let's say, right? And as we study the motion of planets, right, we see some, different eccentricity. I think some things have pretty close to circular orbits, right? But other things like comets might have highly elliptical orbits, right? Anyway, so that eccentricity is important to understand the application of ellipses to elliptical orbits, which of course I think is kind of important for anybody who's interested in science and understanding the world and such. So there's that. Hyperbola. Hyperbola is also defined in terms of distances. So here you have two focal points again, or two, whatever. And so there, what we insist is that the difference between d1 and d2, d1 minus d2 is held fixed to a constant of 2a. So the difference between the distances is held fixed in a hyperbola. And a standard equation is x squared over a squared minus y squared over b squared equals to 1. By the way, all of these standard equations are derived in this section. If you read section 10.1, you'll come to a deeper understanding that I'm currently trying to give you. He actually explains a little bit more the nuts and bolts of where these equations are coming from, so you can read that. If I hadn't spent so long on series and sequences, I would have probably done that in class. Oh well. And let's see, the other important thing for hyperbolas is, of course, the vertex. Two vertex in this case, right? A0 and 0 and minus A0 in the case that the hyperbola opens sideways like this. And then, of course, the asymptotes. The asymptotes we can find, asymptotes are when x and y are huge. And so that would mean that basically 1 is irrelevant. So if you set it equal to 0 and solve, you'll get the equations of the asymptotes. And there they are. Those are what the hyperbola approaches but doesn't quite get to. And there is your lightning tour of what conic sections are and their standard equations. Any questions? Yep. Mm-hmm. Sure.
It doesn't affect by gravity. It would decelerate as it gets closer to the planet, and then it would slingshot off. Is there a way to represent that elliptical path mathematically?
I mean, basically you've got the sun. Right? And then you've got this orbital plane, or orbital plane. I don't think orbital plane is right. Orbital plane. I said something wrong. I don't know what it is. And then yeah, you got planets that go in ellipses where this distance is pretty small, whereas that distance is much larger, right? That's something with large eccentricity. And then you have things that have more, like the Earth, right? Pretty small eccentricity, I think, which just go in like circular paths where the eccentricity is basically the radius is the same at different points in the path. And this is my awful picture. Sorry, I should try just to go two-dimensional. That'd be easier. Sun. So you have paths like this, right? But you have other ones that are more like this. And then you have some that are like this. And yeah, when the planet is closer to the sun, it's going faster, right? When it's out here, it's going slower because most of the potential energy is, it's got more potential energy out here. Here it's got the least potential energy, the most kinetic energy. Kepler's whatever law says that equal areas are swept out in equal times, or in more educated terms, angular momentum is conserved. But yeah. Yes, I think it's fair to say that elliptical orbits are important to space travel because elliptical orbits are what comes out of Newtonian mechanics applied to celestial motion. So yeah, they're impossible not to use. Yeah. But yeah, there's this slingshotting stuff that you. Yes. Back to the diagonalization. All right, well, this is not part of this course, but since you brought it up, yeah, it's part of your course, fine. So the question is, you can make a change of variables. All right, like this is x, y equals to 1 s is just saying, if you invent a new coordinate system, like this, all right, and say that this is the x, or I guess this way, fine. Say this is x bar, and this is y bar. In those new coordinates, the equation becomes like the standard equation here. I think, if I remember right, do something like x bar is equal to something like, I don't know, something like 1 over square root of 2 x bar plus y bar, and y is equal to 1 over root 2 x bar minus y bar, something like that. If you do that, if you plug these equations up in there, you get what? So if I change variables to x is equal to 1 over root 2 x bar plus y bar, and y is equal to 1 over root 2 x bar minus y bar, if I plug that equation, these change of variables, into x, y equals to 1, that gives me 1 over 2 times 1 over 2 is 1/2, and then yowzers. And then you multiply those out, the cross terms cancel, right? And you get x bar squared minus y bar squared. And it's still equal to 1 because this is just xy, right? Excuse me. Of course, I don't have that. I have this over what? 2. But there you go. That's manifestly a hyperbola in the x bar, y bar coordinates, which you just obtain by rotating the x, y coordinates by 45 degrees. Standard. But yeah, the thing is we don't know how to construct rotated coordinates in a systematic way in here, so I can't teach this in calculus 2. Sorry. If you learn something, unlearn it. I don't want to have taught you something about this here. So let's just get rid of this. Forget about it. I mean, don't forget about it. This is something you'd like to learn eventually, right? How to do rotated coordinates. But one thing at a time. All right. All right. If you find a really good, like some other calculus, even if you find a really good pre-calculus book, they'll sometimes have the equations for a general like quadratic, including the rotated case. And they'll give you algebraic conditions when the coefficients make it an ellipse, a hyperbola, or a parabola, right? Because if you translate things and you rotate things, the equations get all jumbled, right? I mean, at first glance, does xy equal to 1 look like it has anything to do with this? Not really. But in fact, geometrically, this and that are the same thing, right? It so happens that eigenvalues and eigenvectors resolve this mystery and explain to you why that's the case in a uniform and beautiful way. But again, for linear algebra. All right, so here we go. Next example. This is what? I regret this example. I'm going to fix it. I was missing a 2. Now I'm happier about my life. Yeah, I think it's going to be an ellipse, but let's see how. So I have to put a 2 here, yeah? If I do that, then what? Oh no. So it begins. Yeah, I think I need to be, I don't think I can add, yeah, right, +1. Thank you. So this is 2, let's see here. This is 2 times x squared plus 2x, right? Yeah. Let's see, this one I can do y minus 3 quantity squared, right? Minus 9 equals to 8. But yeah, I should probably factor out the 2 to start with. Otherwise, I'm going to trick myself. You don't want that. Now I'll complete the square in here. That gives me x plus 1 squared, right? Now I just added 1, so I have to subtract 1 to be fair. I add that, that's 17, right? Okay. All right. So then let's clean things up here. This is 2 times x plus 1 quantity squared plus y minus 3 quantity squared is equal to, let's say I have to add 2 to both sides. I get 19 over here. Now to put the ellipse in standard form, I have to divide both sides by 19, right? So this gives me x plus 1 squared, 19 over 2, plus y minus 3 quantity squared, divided by 19, right? But because we know our target is to compare with the standard form over here, right? So I should really think of this as the square root of 19 over 2 squared, you know, and this is the square root of 19 squared. So I have A is square root of 19 over 2, and B is equal to the square root of 19. And if I want to plot this thing, where is it centered? When is this 0? -1, 3, right? Yeah. So this is a translation of the ellipse to this new center. And if you read section 10.1, he talks about translations in a little bit more generality than I am right here. And he derives some nice things with this idea of translation, right? But just getting to the point here. So -1, 3 is what, like here somewhere. And let's see, what's the square root of 19 is what, like 4.5-ish? And this is square root of 19 divided by square root of 2. I don't have a good sense of, I know it's smaller, but I don't have a good sense of 0.7 it. So I guess, roughly speaking, this looks something like this. Very roughly speaking. It's a sad, I think I've just made my ellipse into a bean, but it's okay. We'll allow it. Still better than most of what I grade on your tests in terms of pictures. Yes, you do have to sketch graphs in Chapter 10. This is a chapter on analytic geometry. If I didn't ask you to graph things on the test, it would be rather silly on my part. Yes. Yes, you are expected to take writing utensils, apply them to paper, and create shapes, geometric shapes. This is called drawing. This is something that's required in this course. Yes, I know. What's that?
We're not art majors.
You're not art majors, and yet you will create beautiful art on the next test. In fact, that art will be quantifiably better than what most art majors create. Sorry. It's unnecessary throwing art under the bus. Sorry, I shouldn't do that. They're good people. Anyway. Okay, so that's all I got for you guys on conic sections, pretty much. I mean, there's much more to be said here in terms of how to shift things around, but I thought I'd show you a token example. You work the homework from the section. That should complete your knowledge. If you read the section, we should have what we need. I will spend the lion's share of my effort trying to explain to you what polar coordinates are, and more importantly, how to manipulate and understand parametric equations. That's really the heart of what we're going to do. So this is just a starting thing. So polar coordinates. What's the deal with polar coordinates? What are polar coordinates? Well, my picture has gotten rather cluttered, so let me start over. So I just start with just an XY. Start with an XY axis. All right. And I pick a point up here where we're happy. We usually call that point XY, right? But we can also do what? We can reach this point by going a distance r from the origin, and by sweeping the standard angle theta up like that. Now, of course, what's the r is equal to what? The square root of x squared plus y squared, right? We know that. And if you draw a little right triangle in here, you can see this distance here is what? R cosine theta. And then if you go vertically up, what do you got here? R sine theta. All right. Now, what you're looking at here is, this is a graph, this is theta, right? This is what? This is a graph of sine theta. And this is a graph of cosine theta. And so like here's 180 degrees, or pi radians if you like, Over here is 360. I usually talk about pi radians, but I think since I'm talking about geometry here for a little bit, I will talk about degrees. I think that makes more sense to people. At least it does to me. I don't know. So my point to you is I drew this triangle in the first quadrant, right? And it's certainly true from right triangle trigonometry. You can see the fundamental equations. They're staring right in front of us. X equals to what? Oh, I've got them right here. I'm like, idiot. They're right here. Right there. Yes, x is equal to r cosine theta. Y is equal to r sine theta, right? You can see that from the right triangle trigonometry, right? But you should appreciate that we have defined sine and cosine in the other quadrants, 2, 3, and 4, right? How? Precisely so that the signs, the SIGN of them, match up with the requisite signs of the different quadrants, right? Like you notice that you've got cosine theta and sine theta positive here, right? You've got cosine theta and sine theta negative here. In the second quadrant, we have cosine theta less than 0, but we've got sine theta greater than 0, right? In the fourth quadrant, we've got cosine theta greater than 0. We've got sine theta less than 0. This is exactly what we need for the polar coordinate equations to make sense, right? So these formulas are already set up to implicitly assume the construction of the angle as the standard angle, right? In other words, angle 0 corresponds to the positive x-axis, and then you sweep counterclockwise. If you made angle 0 something other than that, right? If you made angle 0 like the negative y-axis and you swept clockwise, x equals r cosine theta and y equals r sine theta would not be your equations, right? They would be modified with a sine and a shift of an angle or something like that. But these are the standard polar equations, all right? For example, this point, minus 1, 1, minus 1, minus 1, well, that's at 225 degrees, right? That's counterclockwise from the positive x-axis. This is the so-called standard angle, right? I was just telling physics the other day. I would be so delighted if I had a class of physics that carefully understood what the standard angle was and didn't needlessly and foolishly lose points on this simple and trivial task. But in any given semester, I've got at least half the class who, when asked to find the angle of this point, gives me something other than 225 degrees. They give me 45 degrees. They give me minus 45 degrees. Anything but what's right. Yeah.
Standard angle is whatever's positive counterclockwise from positive x-axis.
I mean, I'm not a monster. I'll also accept this plus 360, plus 720.
As long as it goes in this direction.
Minus, if you could subtract 360, that would also be correct. I mean, there is a degeneracy that's allowed.
But it always has to come from positive x-axis.
It has to be measured in the counterclockwise sense being positive. Now, some people are more of a stickler than I am. Like, they'll be like, no, the polar angle has to be measured between 0 and 360. Or other people might say, no, the polar angle has to be measured between like 0 to pi and then 0 to minus pi. One of those included, one of those not included. That's a standard choice of complex analysis, is to sweep to pi and then the minus pi, and that's the standard angle. But
Probably don't want like 36,000.
no, I probably don't, but you know, I shouldn't tell you guys this. I shouldn't tell you what I logically allow, because you might sarcastically take me up on it. Make my grading hard. No, there's no easier way for me to tell that a student hasn't studied than to see neglect of the standard angle. It sticks out like a, well, you know, like a chicken. I was thinking like that guy who drives really slow back from the bar so the cops won't catch him, but he's like weaving at 10 miles an hour in the 40-mile-an-hour zone, you know? To me, it's like that. It's just wanton neglect. But whatever. See, this is why teaching physics is not good for me. It makes me say these things. But I like you guys. I want to say good things about you. So let's not talk about physics. So y equals mx plus b. So the next order of business is like, we have described things in Cartesian equations, right? Like, for example, these. It's completely Cartesian description of conic sections, right? Well, for every Cartesian description, you could come up with a corresponding polar description, right? You give me a point in the plane, there's a unique correspondence between that point in the plane in xy coordinates or polar coordinates. I say unique correspondence, I shouldn't say that. In fact, the polar coordinates are not unique, right? Because of the angle degeneracy we were just talking about. Oh, but it's worse. As you go on in the chapter, he doesn't force, like, this is my default as to not go nuts thinking about cases. But in truth, as we graph polar equations, they will allow r to be negative as you go on here. And this is the custom of Calculus 2, but not Calculus 3. I know, right? It's nuts, but it's true. At least me, when I'm in Calculus 3, I try to keep r positive or non-negative, because allowing r to be negative is just annoying. But sometimes it's convenient. Anyway, we'll talk more about that some other day. Let me not get into that at the moment. We'll have to get into that as we graph polar equations, all right? I'm doing something simpler at the moment. I'm just converting a Cartesian equation to a corresponding polar equation, all right? How do you do that? Really simple. You take your given Cartesian equation, right? Anywhere you got a y, you replace it with r sine theta. Anywhere you got an x, you replace it with r cosine theta. That's it. And then our custom is to solve for r to describe the polar equation. So I just solve for r. It gives me r is equal to b over sine theta minus m cosine theta. There's the equation for a line in polar coordinates. Now, isn't that weird? But it kind of makes sense, right? Because if you think about a line, right, as you... Man, I can't draw anything today. As you vary theta, right? As theta varies, the radius, you see the radius changes, right? But it changes in a rather complicated way, right? So there's the equation of a line in polar coordinates. Do you like it? I personally don't like it. I think it's ugly. But that's because lines do not have their home in what? Right, I mean, polar coordinates, it's a place for circles and things that are natural in polar coordinates, like arcs or rays from the origin, right? Hey, what happens to this when we have a ray from the origin? What would that be? Say y equals like mx. Then you get what? R sine theta is equal to m times r cosine theta, right? Which gives you what? In other words, you can't, I mean, you can't really solve for r as a function of theta when a line goes through the origin, can you? Theta is fixed. It's the inverse tangent of m, right? Well, with appropriate adjustments for angles and such, but m is equal to tangent theta. That much I can say without reservation. But that's a weird case, right? That formula isn't necessary in the case m. In case b equals to 0, so look at that. So if you just foolishly followed this, what would this trick you into thinking if you put b equal to 0? You'd get r equals to 0. Yeah, that's obviously not true, right? The reason that it's not, I mean, that derivation has division by 0 in the special case, so it's not valid. You can't divide by sine theta minus m cosine theta, in this case that it's a line through the origin. That is 0. This thing is 0. You cannot divide by it in the case that b is equal to 0. Anyway, I guess either you have that 0 or you have r is equal to 0. If you think about it, if b is 0, right? R equal to 0 gives the origin. M equal to tangent theta, that describes all the other points on the line through the origin. All right, I'm going to stop making this example more confusing for you guys. Trust me, what I'm saying makes sense if you just stop and think about it for a while. Now this here, my second example, x squared plus y squared equals to r squared, you plug in r cosine theta, plug in r sine theta, right? You factor out r squared, you got cosine squared plus sine squared, but that's 1. That gives us little r squared equals big R squared. But big R squared is a constant, all right? A given constant. But it's positive, so you can solve r is equal to r. In other words, it's a circle. So that means that this distance r is equal to r all the way around. To me, that is a better description of a circle than x squared plus y squared equals to r squared. It's closer to what it really is geometrically, right? in polar coordinates, r is the distance from the origin, right? The equation r equals to r says, hey, you're looking at the collection of all points that is fixed distance r from the origin. It's a circle. What do you guys think? I mean, I'm not saying anything terribly deep here. I'm just telling you circles are natural in polar coordinates. How much time do I have left? I have left my phone. 3 minutes? All right. How many? I got 3 minutes. I heard 20 minutes. Which one was right? Oh, man. Why doesn't time ever go the other way? All right. Here we go. What I want is I want to rewrite this guy in terms of eccentricity. So we've got x squared over a squared plus y squared over b squared equals to 1. What's the relation between b and a and c? There's a relation, by the way. B is equal to what? If you look at the derivation of the standard equation, we learn that b is equal to the square root of a squared minus c squared. All right? We also have that e, the eccentricity, is defined to be c over a. What I would like to do is to rewrite the equation of an ellipse in terms of eccentricity. So let's see here. We've got r squared cosine squared theta divided by let's see here, a squared plus r squared sine squared theta, b squared. Well, b squared is what? B squared is equal to a squared minus c squared. That's equal to 1. All right. Now, if I want to keep, which one do I want to, let's see here. What do I want to get rid of? I guess I'll keep the c and get rid of the a. How about that? C is equal to what? AE, right? So we can factor out r squared. We've got cosine squared theta divided by a squared, but we're keeping the a. Okay, a squared. Plus sine squared theta. A squared minus c squared is what? A squared minus a squared e squared, yeah? And so let's see here. Of course, I have r squared over a squared times what? Times cosine squared theta plus what? Sine squared theta over what? 1 minus e squared equals to 1. If I multiply this whole thing by 1 minus e squared, I get r squared over a squared times 1 minus e squared cosine squared theta plus sine squared theta equals to 1, which gives me r squared over a squared is equal to 1 over what? Oh, what could I do here? I've got a 1 times the cosine squared theta and the sine squared theta. That adds to be what? 1. So what I really have is 1 minus e squared cosine squared theta, right? The 1 from the sine squared plus cosine squared, and then I still have the residual e squared cosine squared theta. And so I get r is equal to a over the square root of 1 minus e squared cosine squared theta. And there you go. That is the polar equation of an ellipse in terms of its semi-major vertex A and its eccentricity E. When the case that we have E is equal to 0 of a circle, this reduces to R equals to A, which of course is the radius. It makes sense. Woohoo! And that will explicitly define for you in terms of the eccentricity of the orbit how far away it is at a given angle as it sweeps around, which is interesting. This should be in the bulk of the section. If I was to write a calculus book, this would be in the body of the text. Anyway. Thanks, guys. Have a good weekend.